Okay, a nice pretty short section. 1.4, we're going to be talking about exponent properties and how to combine exponents together, simplify down expressions. So they're all kind of listed out here. We need to know that when we have an exponent on the outside of a set of parentheses like that, we're allowed to bring that to the inside, get rid of our parentheses, and multiply these exponents together. Now, if we have two of the same base, we are allowed to add those exponents together, because remember, what an exponent means is that many copies of the base multiplied together. Now, if we had a couple different things on the inside of a set of parentheses, you have to remember that that exponent on the outside, it's kind of like it gets distributed or multiplied by each one of those exponents on the inside individually. Sometimes it's easy to forget that each one of those, like the a is raised to the first power and the b is raised to the first power. Something very similar occurs over here where we have a fraction. That exponent from the outside, the m, gets multiplied by each of the exponents on the inside. Negative exponents. This is one that students typically aren't quite as comfortable with as some of these other exponent rules. When you have a negative exponent, we're allowed to get rid of that negative and make it positive by kind of changing from, if we're in the denominator, we're allowed to move that up to the numerator and make it positive, because this would be like over 1. Or if you have your negative exponent and it's up in the numerator, the a to the negative m power here is up in the numerator, you're allowed to move that down to the denominator and make it positive there. Now we're going to use this property in reverse later on this semester as well, where if you have something in the denominator, we want to get comfortable with being able to move that up to the numerator and rewrite it with a negative exponent. Now anything raised to the 0 power is always equal to 1. And then radicals. Okay, we can rewrite a radical. This is a raised to the m power, and it's underneath a radical of index n. So if you want to write that with a rational or fractional exponent, the exponent goes as the numerator, the index on the radical goes as the denominator. So this definitely comes in handy if we see if we have a square root of x. A square root automatically means index here is going to be 2. All right, so rewriting a square root would be x raised to the 1/2 power. Now the one that I kind of left out here off to the side is if we were to have the same base in the numerator and in the denominator. Now a lot of books write this out as you want to just subtract your exponents, which is correct. However, I like to think about it as kind of two quick, easy questions. I like to ask the question, where do we have more and how many more? So what I mean by that is, like if we had x to the 4th over x squared, that should be x just raised to the 2nd power as we reduce down using that subtraction rule. But how I like to visualize it is, I think to myself, 1, 2, 3, 4 copies of x up in the numerator, and 1, 2 copies of x multiplied together in the denominator, because remember that exponent means that many copies multiplied together. And then I start pairing them up. I say, well, if I have an x over an x, that makes a 1. An x over an x, that makes a 1. So, back to my questions. Where do we have more, and how many more? Well, in this case, we have 2 more in the numerator. So that's going to be x squared left in the numerator. All right, let's jump into some more examples. All right, so first of all, if we have 3x times 7x cubed, we can multiply our constants together. Right? We have 3 times 7, make that 21. And then we can deal with the x's by themselves. Now they're on the same level, so scroll back up here. This is going to be the rule in the top right in this box. Same base, and we want to add those exponents together to combine them. So we're going to get x to the 4th power. Remember that x in the first set of parentheses had a 1 as its exponent. Let's move down. Now this next one, we have a couple different options on how to approach this. One option is you can write 2 copies of that set of parentheses next to each other. All right, that's what an exponent means, is that many copies of the base multiplied together. And then it looks very similar to that previous problem that we just worked. We can multiply the 2's together. 2 times 2 is going to make 4. And we can add our exponents to combine the x's together. All right, x cubed times another x cubed, that's going to be x to the 6th power. Now we do have another option if we would like to use that, and that's using the rule where you have an exponent on the outside. I'm thinking this rule or this rule, where you have an exponent on the outside, you're going to multiply each of the exponents on the inside by the exponent that was on the outside. So it's important to remember that 2 is raised to the first power. This is where everyone makes their mistakes, is the 2's raised to the first power, so that 2, you can kind of think of it as distributing, gets multiplied by each one of those exponents on the inside. So that would give us 2 to the second power, 1 times 2 for the exponent, and then 3 times 2 for our exponent there. A little bit of reducing down, and you get the exact same answer as we did on the left. 2 different ways to think about it, but I think we should get used to multiplying the exponents on the inside by the exponent on the outside. All right, let's take a look at that cube root over on the right-hand side. Let's first rewrite this as a fractional or rational exponent. So to do so, I'm going to say 5x to the 6 y squared is all going to be raised to the 1 over 3 power, the 1/3 power. Now, again, line up our index on this radical goes as the denominator on our fraction, and you could have said this whole thing is raised to the first power if you wanted to, like put a 1 out here on the outside, it's all raised to the first power. That's why our numerator on that exponent is a 1. All right, now to bring that exponent to the inside, it's going to use that rule we just used again, that basically you can think of this as you need to multiply each one of the exponents on the inside by 1/3. Where everyone makes their mistakes, though, is they forget that 5 is raised to the first power. So that'll be 5 raised to the 1 times 1/3 is 1/3. X raised to the 6 times 1/3 power. Y raised to the 2 times 1/3 power. Now we can do better than leaving that as 6 times 1/3 and 2 times 1/3, though. I think the best final answer, I would probably leave this as 5 raised to the 1/3. X raised to the, 6 times 1/3 makes 2. And y raised to the 2 times 1/3 makes 2/3. All right, one more here. When you have a big fraction like this, everything's multiplied together, and that's important as we do these. We don't have separate terms that are connected with addition or subtraction. These are all being multiplied together. So as we do these, the exponent rules don't really work nicely if you have separate terms like addition or subtraction in between. So make sure everything is multiplied together like what we have. So in a fraction, what we are allowed to do is we could split this apart. Now I'm not going to advocate that we actually rewrite this as separate fractions, but this is kind of my thought process, that because everything's multiplied together, we are allowed, if we wanted to make this 3 individual little fractions that are all multiplied together. All right. Now, on each one of these, I would not rewrite these, but we know how to combine fractions together. You just multiply numerators and you multiply denominators, so that one big fraction actually could be thought of as 3 individual little fractions. So I'm going to deal with these on one at a time, basically, and say, well, I know how to simplify down 15 over 45, deal with the constants by themselves. That's going to make the same thing as 1 over 3. And then I would move on to the a's and deal with those. This is that situation where I ask myself, where do we have more and how many more? So in this case, we have more in the numerator and we have 2 more, right? 5 minus 3 makes 2 left in the numerator. And then one more here, we have the b's to deal with. Where do we have more and how many more? Well, we have more in the denominator and more by 6. All right, we wouldn't have to leave that 1 up in the numerator as a placeholder because we have the a squared up there. If you had done it with the separate fractions, that would be okay too, right? We'd get the 1/3 times a squared, maybe over 1, times 1 over b to the 6th power. Combine those back together and we get the same exact answer. All right, so I hope this helps out. That's a good place to stop for this video. Good luck. Keep practicing on these. They really pay off for future lessons when we get more into the calculus side of things.